Sciences, University Science Malaysia. This year theme of this event is Advancing Innovation in Chemical Sciences for Sustainable Development in COVID-19 era, focusing on the chemistry aspect in energy, food, health, and environment.
To attract participants from all over the world, the Department of Chemistry Universitas Gadjah Mada collaborates with the School of Chemical Sciences, University Science Malaysia, the Royal Society of Chemistry, and the Indonesian Society of Chemistry. There are 4 keynote speakers in this conference from Indonesia, Malaysia, Japan, and Thailand. Also, there are 4 invited speakers from Germany, South Korea, Singapore, and Indonesia.
All presented abstract will be featured in the Book of Abstract. Selected works nominated by the committee will be published in scientific.net, a Scopus Index conference proceeding edited by reputable scientific boards. Before we start our session, participants should follow the conference guideline. First, participants are expected to be present in the virtual room no later than 10 minutes before the event starts.
Second, participants are expected to remain silent or muted until they're allowed to speak by host or moderator.
Third, participants are expected to ensure that they have enough bandwidth to participate in the conference.
Fourth, participants are not allowed to record the program in any forms because the content of this conference is protected by copyrights.
Fifth, participants are expected to use their full name on the account used in accordance with the name during the registration. Participants are required to change the user's name by adding parallel ulung code. For instance, Adi Herman will be engaged in Gamma Room. Then he should change his username as G_Adi Herman.
6, participants who are registered as non-presenters are allowed to choose which breakout room to join during parallel sessions. That is the information of the conference. The session will begin shortly. Thank you. Good morning, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. Welcome back to the 4th International Conference on Chemical Sciences, organized by the Department of Chemistry, Faculty of Mathematics and Natural Sciences, Universitas Gadjah Mada, and School of Chemical Sciences, University Science Malaysia. The agenda for the second day is the plenary session, the parallel sessions for presentations, also the last is the closing.
Ladies and gentlemen, welcome to the second day of 4th International Conference on Chemical Sciences. First of all, let us praise to God because of His mercies and blessings so we can gather on such a beautiful occasion this morning. My name is Fadli.
My name is Katie.
It is being a great honor for us to be standing here as the Master of Ceremony for today's event.
Before we proceed with the program today, we would like to express our sincere gratitude to our keynote speakers, Professor Yuichi Kamiya from Hokkaido University, Japan, Professor Pranut Patiara, PhD from Chulalongkorn University, Thailand,
Our invited speaker, Professor Yonggun Ko from School of Material Sciences and Engineering, Yungnam University, South Korea, Dr. Bambang Purwono, MSc from Universitas Gadjah Mada, Indonesia,
our sponsors, PT Spektakrom Indonesia,
PT Teknolab Indo,
Indonesian Natural Dyes Institute, Universitas Gadjah Mada,
PT Gincraft,
PT Ditek Jaya,
and PT Era Mitra.
and all the excellent presenters, all participants, ladies and gentlemen.
Now we are going to the next agenda. We are about to hear the third keynote speech that will be delivered by Professor Yuichi Kamiya from Hokkaido University, Japan. The keynote speech will be moderated by Professor Dr. Nuryono, MS. Now, please welcome Professor Dr. Nuryono, MS. Professor, the time is yours.
Thank you, Miss MC, Mbak Kati, and Mas Farhan. Fadli, sorry. Could you hear my voice?
Yes, we can hear it, sir.
Okay, thank you. Yeah. Dear participant, good morning, and especially Professor Kamiya, good morning, and thank for the join this ICC conference. And before time for Professor Kamiya, allow me to read maybe on the short curriculum vitae from Professor Yuichi Kamiya. Professor Kamiya graduated in March 1995 from Nagoya University for the Bachelor Engineering, and then 1997, Master of Engineering from the same university, and then March 2003, they got a Doctor of University from the same university, and then professional experience. 1997 as a researcher in Tonen Chemical Company Limited, and then 2002 as a researcher fellows in Japan Society, and then 2003 associate professor at Faculty of Art Science and Hokkaido University. Yeah, and then in 2015 as a professor at the same faculty of Environmental Earth Science, Hokkaido University. And then talking about the publication, I don't want to read all because right now more than 100 publications have been paper have been published based on the Scopus data, and he has it's index 22 right now. And next, okay, and then the research interest of Professor Kamiya, catalytic chemistry and catalytic engineering for water purification. And then he also do research in design of heterogeneous catalyst based on regular assembly of a well-defined metal and metal oxide cluster. Yeah, right now in 2021, he has already published 5 paper, I think. And then besides that, he also have already published some books and also another publication. You can see that there are 5 book and other publication. Yeah, I don't want to read. Yeah, because this can be read by yourself. And then also, yeah, right now he have 4 current research project. Yeah, of course, he will always involve the student, and he's also got research funding award from Petroleum Society and in 2007, and then also as Young Science Prize of International Association of Catalysis Society 2004. I think that's all for the curriculum vitae. Yeah, I don't want to read because it takes a long time. So right now, the time belongs to you, Professor UC Kamia. Please deliver your presentation. Thank you.
Okay, thank you very much, Professor Nuriono, for very, very kind introduction. So first of all, I would like to express my sincere appreciation to the organizing committee to giving me this opportunity to present our recent topics on the groundwater purification by catalytic and photocatalytic reactions. Okay. No, sorry. So please wait for a moment to arrange. Oops. No, 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 no. Okay. Okay, so the topic of my talk today is catalytic and photocatalytic
Water pollution with nature.
reactions for purification of groundwater polluted with nitrate. So in my talk today, I will talk what went well and what was achieved, and also what are remaining problems to be solved, and what are challenges for us to treat real groundwater polluted with nitrate by catalytic and photocatalytic reactions. So first, let's begin with thinking about clean fresh water. So this is a good picture for us to image clean fresh water. Of course, we need clean fresh water to live, to manufacture industrial products, to grow crops, to raise farm animals, and so on. So it is obvious clean fresh water is indispensable matter for our society now and in the future. As a water resource for clean fresh water, groundwater has great advantages. One advantage is good quality. Normally, groundwater is drinkable. without any treatment. In addition, groundwater is easily available and abundant. A great advantage of groundwater is little change in water volume throughout a year, which is quite different to river water, especially in Japan. So effective utilization of groundwater is indispensable to ensure clean fresh water. However, recently, pollution of groundwater with nitrate has become a serious problem throughout the world. If people drink water containing high concentration nitrate, ingested nitrate is reduced into nitrite, NO2- in the stomach. The nitrite is absorbed in the blood and reacted with hemoglobin in red blood cell. Such hemoglobin cannot transport oxygen anymore, and so the person shows cyanosis. Because babies are very sensitive for nitrate ingestion, this symptom is called blue baby syndrome. As you know, about 100 years ago, Harvard and Bosch developed a method for industrially producing ammonia from nitrogen in air. Because nitrogen is very important nutrient for plant, a lot of nitrogen fertilizer is produced from ammonia. So this invention saved people from the food crisis, and this invention has still been supporting population growth and population explosion. However, the excess utilization of nitrogen fertilizer causes various environmental problems. One of those is pollution of groundwater with nitrate. The most effective measure to resolve environmental pollution is removal of the pollution source from environment. However, it is difficult for nitrate pollution of groundwater because nitrogen fertilizer is indispensable to effectively produce agriculture product. So the polluted groundwater must be purified if people drink the polluted groundwater. One promising method is catalytic reduction of nitrate into nitrogen in water. About 30 years ago, the catalytic reduction of nitrate in water was firstly reported by German group. In the catalytic reduction of nitrate, the formation of byproduct ammonia is an essential problem. As you know, ammonia has bad odors, and people cannot drink water containing ammonia if nitrate is disappeared. So the ammonia formation must be suppressed to acceptable level for drinking. In other words, the catalyst must have high N2 selectivity for practical application. However, there were only few catalysts and catalytic reaction systems to satisfy the high nitrogen selectivity and low ammonia selectivity when we started our study on this topic. Here is a typical catalytic performance of bimetallic palladium catalyst. Because catalyst should activate hydrogen at around room temperature, a precious metal like palladium is necessary. However, the precious metal itself cannot activate nitrate. So the second metal is necessary to activate nitrate for the catalyst to show the catalytic activity. Among various combinations, the palladium copper bimetallic catalyst was the best combination in terms of the catalytic activity. In addition, the copper palladium combination showed low selectivity to ammonia. In other words, the high selectivity to nitrogen was achieved over the copper palladium bimetallic catalyst. So the copper palladium bimetal was a promising candidate for active component of the catalyst. However, the just simple combination of palladium and copper did not meet criteria for drinking water because the selectivity to ammonia was still insufficient, around 50%. So our first motivation was to develop copper palladium catalyst, which shows sufficiently low selectivity to ammonia, hopefully the below 2% or less ammonia selectivity. In other words, we tried to develop the catalyst showing high nitrogen selectivity. The target was very clear, high nitrogen selectivity and low ammonia selectivity. But our challenge was how to design the copper palladium catalyst to further decrease the ammonia formation. To get an idea for the catalyst design, first we considered the reaction mechanism of the copper palladium catalyst. As shown here, the reaction was known to proceed sequentially through nitrite as an intermediate. In the first step, from nitrate to nitrite, the reaction occurs on the copper palladium bimetallic site. Hydrogen is activated on the palladium site. On the other hand, nitrate is reacted with metallic copper to form nitrite. After that, the formed oxidized copper oxide is reduced by the reaction with hydrogen activated on the palladium site to complete the catalyst cycle. The formed nitrite is further reacted on the palladium site. In this reaction step, copper is unnecessary. The reaction of nitrite on the palladium site is selectivity determining step because this step determines which products are formed. In this reaction step, the atomic nitrogen or nitrogen oxide is formed on the palladium site as an intermediate. As shown here, so if such nitrogen intermediate is reacted with hydrogen, ammonia is formed. On the other hand, the reaction of two nitrogen intermediate results in dinitrogen formation. So based on such reaction mechanism, a simple idea arose for us how to proceed with the catalyst development. Our idea is if hydrogen, low hydrogen concentration and high nitrogen concentration on the palladium site shown here was achieved, the catalyst would show high N2 selectivity. Conversely, the catalyst with high hydrogen concentration and low nitrogen concentration may show high ammonia selectivity. To make such situation on the palladium site, use of low pressure hydrogen, in other words, diluted hydrogen would be effective to reduce the surface hydrogen concentration. In addition to the controlling the reaction conditions, we thought that a well-mixed copper palladium structure would be a good catalyst for low ammonia selectivity. As I told you before, hydrogen on the palladium site are consumed to reduce oxidized copper site on the catalyst. So if all palladium sites are located next to copper site like this, the low hydrogen concentration on the palladium site would be achieved under the steady state reaction conditions. To demonstrate this idea, we prepared two catalysts with typical structures. One is a catalyst in which copper and palladium are well mixed. The other is a catalyst with segregated structure in which palladium domain, copper domains are segregated, and only limited number of the copper palladium sites are formed at the interface between the two domains. So we evaluated the catalytic performance of these two catalysts with typical different structures. The well-mixed structure catalyst was prepared by the reduction of palladium 2+, copper 2+ with iron sulfate in the presence of sodium citrate. After the reduction was completed, the formed copper palladium bimetallic cluster was fixed on the activated carbon. Here is the TM image of the catalyst. Small nanoparticles with around 5 nanometer in size were clearly observed and uniformly dispersed on the catalyst support. The XRD study demonstrates that copper and palladium were well mixed in this catalyst because the diffraction line was shown between the copper FCC and the palladium FCC structures. In addition, the well-mixed structure was confirmed by X-ray, extended X-ray adsorption fine structure EXAFS analysis. A segregated structure catalyst was prepared by a conventional impregnation method, and palladium and copper were added to the active carbon step-by-step manner. As shown in this XRD pattern here, both palladium FCC and copper FCC structure were clearly observed in this segregated structured catalyst, demonstrating the formation of the segregated structure shown here. Next, we performed the catalytic performance of nitrate over the two catalysts. Here is the catalytic reaction data. First, the catalytic reaction was performed with 0.5 atm hydrogen. As we expected, the well-mixed structure catalyst showed the high selectivity to N2 and high catalytic activity due to the large number of the copper palladium bimetallic site. On the other hand, selectivity to ammonia was high for the segregated structured catalyst. So the reaction data demonstrate the well-mixed structure is effective to give the high activity and high selectivity for the nitrate reduction. However, the selectivity was still insufficient. So to further improve the selectivity, next we performed the reaction with low pressure hydrogen at 0.05 atm. Under these reaction conditions, ammonia formation was almost completely suppressed, while the reaction rate was decreased. Based on this data, we concluded the well-mixed copper palladium alloy catalyst and use of low pressure hydrogen can achieve selective reduction of nitrate into N2 in water with almost no formation of ammonia. Next, we investigated the stability of the catalyst. The stability test was performed in a continuous flow reactor shown here. The catalyst was put in a glass reactor. Aqueous nitrate solution and hydrogen diluted with helium was fed into the reactor. To neutralize carboxy ion formed by the reaction, carbon dioxide was also fed to the reactor. At outlet, the aqueous phase and gas phase were separated and analyzed individually. The formed small amount of nitrous oxide, N2O, was decomposed by the reaction with hydrogen over the supported palladium catalyst shown here. This is a time on stream result. As you can see here, the catalyst shows a high stability for the reaction. Almost no change in the activity and selectivity were observed up to at least 50 hours. Of course, almost no ammonia formation was achieved for a long time. So far, I told how we succeeded the highly selective catalyst for nitrate reduction in water. This topic has been intensively studied by many research groups, including us. Here is a trend of the number of papers on this topic. The goal of these papers is purification of groundwater polluted with nitrate. However, in almost all papers, aqueous nitrate solution prepared by dissolving reagent sodium nitrate or potassium nitrate in pure water was used as a reaction solution. In other words, only little paper deals with real groundwater polluted with nitrate. As you know, the real groundwater contains various matters, and those may affect the catalytic performance. As I hoped, those makes a positive effect on the catalytic performance, but actually it was opposite. This table shows a component of polluted groundwater, which was taken in rural area in Hokkaido Island. The groundwater contains some mineral component, including chloride, sulfate, silicate, and cations. In addition, water-soluble organic matters were also present in the groundwater. So it was expected those matters made negative impact on the catalytic performance of our developed copper palladium catalyst. In fact, the catalytic performance was severely decreased in the groundwater treatment. Here is the catalytic result for the groundwater treatment by using our developed copper palladium catalyst. To obtain stable performance, aqueous nitrate solution was fed to the reactor for initial 30 hours. Of course, the catalyst shows a high catalytic performance, high activity, and high N2 selectivity. At 30 hours, the reaction solution was changed to the real groundwater. Just after changing the reaction solution, the significant drop of nitrate conversion and N2 selectivity was observed. At 65 hours, the reaction solution was changed from the groundwater to the aqueous nitrate solution, but the catalytic performance was not recovered, indicating the severe irreversible catalyst deactivation in the real groundwater treatment. After our intensive investigations, we found that there were two causes for the catalyst deactivation in the groundwater. A cause is deposition of water-soluble organic matter on the catalyst. Because water-soluble organic matter have a lot of functional groups to make the organic matter water-soluble. The organic matter strongly adsorbed on the catalyst surface, causing the irreversible catalyst deactivation. However, this problem was solved with pretreatment of the groundwater by oxidative decomposition of the organic compound with ozone or UV light irradiation. The other cause was due to the chloride ion in the groundwater. Chloride ion was adsorbed on the copper side competitively to nitrate. Because the reduction of nitrate to nitrite occurs on the copper side, the competitively adsorbed chloride ion inhibited the nitrate reduction, leading to the activity drop in the groundwater. In addition, such competitive adsorption, hydrogen density on the palladium site was increased because hydrogen on the palladium site was not consumed for the reduction of oxidized copper site. As a result, the selectivity to ammonia was increased. The problem was solved by replacement of copper with tin. Competitive adsorption of chloride on the copper site was unavoidable because this is an essential nature of the copper element. So we started looking for copper-free catalyst. At long last, we found tin palladium bimetallic catalyst. Here is the catalytic performance of tin palladium catalyst evaluated in aqueous nitrate solution in the absence of chloride and in the presence of chloride ion. In contrast to the copper palladium catalyst, the tin palladium catalyst shows a high activity and high nitrogen selectivity even in the presence of chloride ion. Thus, the high tolerance of tin site was demonstrated from this result. Before we performed the treatment of the real groundwater by using the tin palladium catalyst, the catalytic performance of tin palladium catalyst was compared with copper palladium catalyst in aqueous nitrate solution. The reaction was carried out in a batch type reactor shown here. In aqueous nitrate solution, both catalysts, tin palladium and the copper palladium catalyst shows a high activity and low selectivity to undesirable byproduct ammonia. The tin palladium catalyst was a little bit active and selective comparing with the copper palladium catalyst, but the difference was only little. Under these reaction conditions, 100% conversion was obtained at 2 hours for tin palladium and 3 hours for copper palladium catalyst, respectively, and the selectivity to ammonia was 5% or less, regardless of the catalyst. Here are the catalytic data for the treatment of real groundwater. As the data demonstrate, the tin palladium catalyst shows a higher activity and lower selectivity to ammonia than copper palladium catalyst. The nitrate was decomposed much faster for the tin palladium catalyst than copper palladium catalyst. The selectivity to ammonia was also lower for tin palladium catalyst than copper palladium catalyst. However, please pay attention to the reaction time. To obtain the 100% conversion in the real groundwater, about 20 hours was necessary even for tin palladium catalyst. In addition, the ammonia selectivity was also relatively high comparing with the reaction in the aqueous nitrate solution. So these data indicate even with tin palladium catalyst, its catalytic performance has deteriorated in the real groundwater treatment. To clarify the reason for the catalyst deactivation in the groundwater, we removed all cationic and anionic species from the groundwater by using ion exchange resin, and the catalytic performance were evaluated by using the pretreated groundwater. Of course, water-soluble organic matters was oxidatively decomposed before the catalytic reaction. We found cations in the groundwater had no impact on the catalytic performance. However, anions had great impact on the catalytic performance. Here are catalytic performances of the tin palladium catalyst in groundwater, anion removed groundwater, and aqueous nitrate solution. The catalytic performance in the anion removed groundwater was almost the same as that in aqueous nitrate solution. So the anionic species in the groundwater must cause the catalyst deactivation in the groundwater. Now I would like to review the anionic species contained in the groundwater again. The polluted groundwater contained chloride, sulfate, and silicate. The existence of chloride and sulfate was confirmed by ion chromatography. The groundwater might contain silicate, but its concentration could not be determined by ion chromatography, so it was determined by ICCS as a concentration of silicon. Then we investigated influence of each anions on the catalytic performance of the tin palladium catalyst. Here are the catalytic reaction data for tin palladium catalyst in aqueous nitrate solution and those with chloride, sulfate, and silicate. Not as we expected, the catalyst deactivation was not observed in the presence of those anions, but the catalyst was indeed deactivated in the real groundwater. So why? A tip to answer it was found in the reaction in the presence of 3 anions at the same time. As you can see here, when 3 anions were simultaneously present in the reaction solution, the catalytic performance was significantly decreased in activity and also the selectivity. The reason for it was the formation of silicate oligomer in the reaction solution. To investigate the influence of silicate, I used sodium metasilicate, SiO3, sodium 2 SiO3 as a silicate source. Metasilicate was detectable by ion chromatography. However, in this reaction solution, the concentration of metasilicate was decreased after the reaction. This indicates the formation of silicate oligomers in this reaction solution. Such phenomenon is not special. I didn't know chemistry of silicate in water, but chemistry of silicate had been deeply studied because most minerals in the cluster silicate shown here, and the chemistry of silicate is very popular in geoscience. According to papers, basically the silicate monomer is absent in natural water. Instead, dimer, trimer, and oligomers are present in natural water, including groundwater. So those silicate species have large molecular weight and multivalent anions. So those silicate species in the groundwater might be adsorbed on the tin palladium catalyst, causing the catalyst deactivation in the groundwater. So to purify the real groundwater, removal of silicate from the groundwater is necessary by an appropriate manner. Unfortunately, we have not yet succeeded it. And this topic is still our challenge, so I hope to show you in the future. Now I would like to change subject.
Could you speed us, Prof. Camilla, because
Yes.
time will be finished.
Okay,
Yeah.
time is coming. Okay.
Yeah.
Okay, so I will skip this topic, sorry. So now I'd like to summarize my talk. So based on the consideration for the reaction mechanism, we developed the well-mixed copper palladium structured catalyst. This catalyst shows a high activity and high selectivity to nitrogen in aqueous nitrate solution. However, the catalyst was severely deactivated in real groundwater due to the water-soluble organic matter and chloride ion. So to solve the chloride problem, we further developed the tin palladium catalyst. So this catalyst has a high tolerance for chloride ion. So the real groundwater was successfully purified by tin palladium catalyst, but the problem on the silicate in groundwater is remaining. So finally, I would like to acknowledge my student, especially for Dr. Iwan and Dr. Jun Hirayama for his support. And I also thank the Associate Professor Ryoichi Otomo for this project. And I also thank the financial support from Japan government and Sumitomo Foundation. Thank you for your kind attention and terima kasih.
Okay, thank you, Prof. Camilla. I'm sorry I have to stop the presentation because of the time. But I think your presentation is very interesting, and on what you call reaction of a nitrate to become ion and compound that is not toxic, of course, and it is very interesting. Yeah. If you, before I opportune the participant for the presentation, for the question. I just want to inform the participant that Prof. Kamia also right now appointed as a coordinator of a JASO program, I think, since September this year. So I think it's very useful for students from here and from the participant. In case you want to visit Hokkaido University and join to Professor Kamiya to do a short research in this this laboratory. I think that's good opportunity for us. Thank you. Okay. Yeah, I would like to read. Maybe there is a question from participant. No, there is no question. Yeah, I will give opportunity to the participant in case you have a question for Professor Kamiya, maybe.
So, Professor Norio, I found a question from the audience, why the alumina was used as a support.
Oh, yeah, sorry.
Okay.
Yeah, from Ferry. Yeah.
Can I answer
sorry,
this question?
Yeah.
Okay. So because the support material is very important to develop the highly active and selective catalyst. Of course, we tested various kind of support, for example, the activated carbon, silica, titanium oxide, zinc oxide, and so on. So the result demonstrate the tin palladium alumina catalyst was the best in terms of the activity and selectivity. Well, this is due to the structure of the tin palladium catalyst on titanium, alumina support. So if the titanium oxide was used, the tin is strongly adsorbed on the titanium oxide. So the good, well mixed tin palladium structure was not obtained. So on the other hand, if we used silica as a support, the interaction between the metal and the support is very weak. So the large metal particles, palladium large particles and silica tin large particles was formed. So the moderate interaction between the tin palladium and support was the best as a support. So the alumina is the best in terms of the activity and selectivity to make the good structure, tin palladium alloy structure, and the small tin palladium particles due to the moderate interaction between the two samples. Thank you very much for your nice question.
Yeah. Okay. From Devi Agustiningsih. Yeah. Question as about the alumina as a support material. And then there is one more question, Prof. Kamiya from Ferry Muhayani. She is a student, a master student from Gajah Mada University, I think. The question is why Prof. Kamiya use SN metal to replace copper metal? Yeah, why not some other metals?
Yes.
This is interesting question.
That is also
very fundamental question. Okay, please, Prof. Kamiya, to answer the respond.
So, of course, at the beginning, we investigated various kind of combination. For example, the palladium, indium, palladium, rhenium, palladium, platinum, palladium, silver, and palladium tin, and so on, palladium lead, and so on. After that, we found the palladium system is the best.
Yeah, I think this is a long story, Prof. Kamiya, about to choose one metal.
Yeah, so trial and error is the best to find a good catalyst at present. But I hope in the future that we expect the good catalyst by the help of the calculation, DFT calculation, something.
Yeah. Okay. Maybe to the committee. Sorry, there is still one more question from Ibu Siti. I would like to read Prof. Kamiya. Why did the process of catalyst activity with low pressure hydrogen? Thank you.
So of course, the hydrogen is one of the reactant for this reaction. So if we use the low pressure hydrogen was used, the reaction rate is significantly decreased. So the activity and selectivity is a trade-off relationship. Of course, we want to use the high pressure hydrogen to promote the reaction more faster. But if we use the high pressure hydrogen, the ammonia selectivity was increased. So we had to use the low hydrogen pressure hydrogen. So that is the answer. Okay, thank you very much.
Yeah. Okay. Thank you, Prof. Kamia. I think if you still have any question regarding to the presentation of Prof. Kamia, you can read by email maybe. Is that okay, Prof. Kamia?
Okay, of course.
Yes.
Oh
yeah. Okay. Very welcome to accept the email and also question talking about the nitrate catalysis. Yeah. Okay. Because of the time, so I have to stop. And once again, Prof. Kamia, thank you for the nice and also interesting presentation today and the second day of ICCS 2021. And now I would like to deliver the time for MC, Mas Fadli, and also Mbak Kathy. Thank you, and you can continue the agenda.
Okay, thank you very much, Professor Nuriono.
Welcome.
Terima kasih.
Ya, sama-sama.
Thank you, Professor Yuchi Kamiya, for the great presentations, and thank you, Professor Dr. Nurena MS, as the moderator. So, ladies and gentlemen, there are a few sponsors which support this event. One of them is Petagen Craft, and this is the introductions video of Petagen Craft. Please enjoy.
Okay, let me start. Good morning or good afternoon, ladies and gentlemen. So I'm Hendy Dwi Miko from the Thermoscientific Division, PT Engineering Labs Jakarta, as an authorized distributor from the Chromatography and Mass Spectrometry Division. And I will give about the presentation entitled Achieving Worldwide Compliance in Dioxin and POPs Analysis using our high-end technology, which is our gas chromatography, magnetic sector, high-resolution mass spectrometry that have a full worldwide compliance for dioxin and furan analysis, and we also have an alternative technology for analysis dioxin and furan in food and feed using the triple quadruple GCMS also. So before we go to our topic, we want to introduce our company first. Our company provides several sections like the sample prep. We have the automated solid phase extraction, and we also have the automated sample extraction from the solid, and this is called the ISE350, and rocket apparatus, spitfire series, and so on. And then for the chromatography column and consumable, we have also like the sealing filters and process products for extract pesticide, IOs, LC and IC columns, vapor fitting and GC columns. And for the analytical system, we have the atomic absorption spectrometer for ICE3000 series AS that we are capable have the dual atomizer, the flame and furnace in the same unit. And then we have also the ICAP Pro, ICPOS, ICPMS, and also the high resolution ICPMS. And from chromatography and mass spectrometry, we have the HPLC, UHPLC FunQuiz, from, and then ion chromatography, GC, GCMS, GCMS, and so on. And we have the market from the high resolution mass spectrometry. This is the high-end instrument from us, from Thermoscientific. We have also the Orbitrap SRMS, LC, GCRMS, or that we focus today. This is the DFS GCRMS, and we also the software from chameleon chromatographic data system, LIMS system, and also ERMS and GLONS analyzer. Okay, we will cover to the introduction to POPs and the emerging POPs of the consent. We will then go to its application of the instrument, and we offer from Temo to cover this application. And then we will talk about the dioxin analysis using magnetic sector with the thermoscientific DFS, and also dioxin input using the triple quadruple GCM-SMS, and also the PBD analysis and SCGP analysis as the persistent organic pollutant. So, what are persistent organic pollutants or POPs? POPs are toxic and bioaccumulate in humans, and so the humans are exposed to POPs from the food and environment. And there is a regulation, the Stockholm Convention, regulates the use and monitoring of POPs. One of the most notorious account of exposure of TCDD was the Victor Yushchenko. Who was exposed to the compound purposely when eating soap. This caused the core acne, and this TCDD was also the active compound in the Agent Orange in Vietnam War. These compounds are still detected today at high level in that country decades later. And there are a number emerging of POPs of interest, namely two on the slide. This is the PCDD, PCDF, so the POPs CCP analysis, and there are many challenges to the POPs analysis. Yeah. We must have an instrument that can hit the sensitivity level required by the legislation, as well as be able to deal with the varying methods and expanding the compound list. Results must be consistent for the reporting the correct limits. And so let's look at the analysis of dioxin with the thermoscientific DFS. It's a magnetic sector GC high resolution mass specs. It has been especially designed for the dioxin and POPs analysis. And why DFS is the gold standard for dioxin and POP analysis. As the gold standard for the dioxin POP analysis, the magnetic sector offers you both compliance with any official dioxin analysis method and regulation, and also for any type of sample, including the food or the environmental. DFS also completely established and renowned in the global scientific dioxin community for its superior performance in routine quantitative analysis of the dioxin and POPs. And also the DFS magnetic sector GC high resolution mass spec offers the proven sensitivity in combination with the highest robustness for the confident results, and we have also the unique dual GC configuration. And this is the EPA 1613 has a strict compliance, including the 10,000 resolution with static resolution. The spectrometer is able to measure compound at the same resolution, and we can also perform the resolution check at the beginning and the end of the 12-hour shift. And we also have to perform the mass dip correction using the perfluorokerosene to provide the log ampere. And also the requirement for the mass window, time window also. And this is our proof of spec, the 20 femtogram of the 2379 TCDD, the signal to noise 200 by 1. This is the highest sensitivity, including in the term of the dioxin analysis. And this is also the example of the reproducible data at the end of the detection limit from our customer lab in Japan. And also we are ready for a longer time. We could do better than the old spec, and this measurement was done 1 year after the introduction of the DFS. This so that we can hit the towards legislation for the examples dioxin in baby food, which have a very detection limit. And this is the technology based on magnetic sector provides a solution for maximum productivity in terms of number of samples analyzed per year. With dual data XL option, you can double your throughput even with the mixed applications such as the dioxins, PCBs, PBDE, OCPs, and other. And magnetic sector high resolution GCMS is the gold standard, and already for decades has been proving its proficiency in this field of analysis, and thus became established analysis technique available nowadays in the leading dioxin laboratories throughout the world. And this technology is can perform the two gas chromatograph to one single MS strongly increase the flexibility, and we can use the dual column adapters to enable the installation of the two column within the one single GC. And then in combination with a dual GC setup, 2, 3, or 4, maximum 4 columns can thus be connected to one single mass spec. In this way, the analytical system can be constantly prepared to perform different applications like a PCDD, PCDF, PCB, PBDE, and etc. And then changing automatically between columns with the measurement of the sequence. So in 2014, a significant change in European Commission regulation was made, and allowing this chromatography triple quadruple or TCMS-MS to be used as an alternative to gas the chromatography high resolution mass spec for the confirmatory analysis and the control of the maximum level and action level in certain only food and feed samples, and providing the certain criteria of performance are met, like the chromatographic separation of beta furans is better than 20% speed to peak, and two specific ceramic transition, and ion ratio and resolution. Yeah. And in particular, the performance of the new advanced electron source has been demonstrated in the terms of the enhanced sensitivity, and also thanks to the higher ionization efficiency to a complete source redesign, including the new filament and magnet positioning. Yeah. And the enhanced robustness towards contamination thanks to the inland ionization producing a much more focused ion beam inside the source, so that the ions are less willing to burn on the metal surface. Okay, and however, in the speed of the stability of the TSQ9000 thermo GCMS-MS has been already demonstrated, there was like a robust data and to validate the suitability on long-term for routine purpose. At PitCon about 3 years ago, we released the dioxin analysis based on the TSQ9000 GCMS-MS after a long-term validation process with hundreds of samples to test and demonstrate the robustness required by routine laboratory for dioxin furan in food and feed analysis. And this is the overlay extraction ion chromatogram, or XIC, are displayed. This is the quantification and confirmation ions for the selected TCDD, hexa-CDD, and octa-CDD congress. And all ion ratios as displayed, and RFs were within the allowable tolerance, about the 15% for ion ratio, and RF less than 30%, as defined by European Union RF guidance throughout the sequence. And the sensitivity achieved with the TSQ9000 advanced electron impact allow for upper bound WHO, PCDD, PCDF, TAQ values were lower than 1 per 5 ml recommends for the most challenging methods. And this is the toxic equivalency factor, or TEF, express the toxicity of dioxin furans and PCBs in the terms of the most toxic form of dioxin, the 2378 TCDD, and the toxic equivalence, or TEQ, report the toxicity weight mass of the mixture of the PCDD, PCDF, PCB, and the reported value provides toxicity information about the mixture of the chemical and is more meaningful to the toxicologists, and then reporting to the total number of grams. And to obtain the TEQ, the mass of each chemical in a mixture is multiplied by each TEF, and is then summed with all other chemicals to report the total toxicity weight mass. And then TEQ are then used for risk characterization and management purpose, as a prioritizing area for cleanup. And in order to further assess the robustness of the system, the remaining extract from the non-ortho PCB and PCDD, PCDF samples was put together into mixed matrix extract, and this pooled matrix sample was then alongside non blank and LOQ standard injection like this. And this is the LOQ RF deviation upper plot calculated as a deviation from the target amount, and ion ratio lower plot, for the 10 femtogram on column 2378 TCDD congruence, The concentration is 2.5 femtogram per microliter, and with the 4 microliter injection volume. And this is the application note for dioxin analysis for feed and food. Yeah, if you are interested, you can Google and you can easily to download it. Yeah. And also the major complex metrics in chromatography challenge for PBD analysis are sensitivity and selectivity resolution and of critical phase degradation of higher brominated compounds and the cost per samples. Also, we have another GC-IRMS for analytical technique of choice for PBDE determination in food, and triple quadruple GC-MS instrumentation has particular recently become more popular for this application to its high selectivity. And this is again of those of you if interested in more detail, you can find them in this application note, which can be downloaded from the Thermo Fisher Scientific website. Yeah. And also we have also the GC of detail also be able to hit very low levels of the detection in matrix tuna. In this case, we are looking at the 0.0 nanogram per gram in tuna with excellent sensitivity. Okay, this is a isotopic pattern, yeah, for identification in the complex environmental sample. And then finally, let's look at the hot new compounds that are very tricky to analyze, SCGP, like blood black pigs and have a lot of congruence. And not only SCGP are being analyzed, but PCB and pesticide as well. And looking at the SCGP in the negative chemical ionization is another way to increase the sensitivity and selectivity for these compounds using the GC high resolution mass spec. And this is the excellent compound linearity from the 25 until 5000 ppb was obtained for this C10 chlorinated homologs present in the SCGP 63% chemical mixture. And this is the detection limit 20 to 25 ppb. And this is the summary. The analysis of POP is of challenging and varied application, and legislation has changed allowing methods to be run artificial instrumentation and thermo offers instrumentation to meet the all requirements for current further analysis.
Ladies and gentlemen, now we are continuing our program to the next programs. That is to hear the third invited speech that will be delivered by Professor Yong-Gun Ko from School of Material Science and Engineering from Yongnam University, South Korea. In this session, the invited speech will be moderated by Associate Professor Dr. Riza Razali. Excellencies and participants, please welcome Associate Professor Dr. Riza Razali. Sorry, Professor, your camera looks like in reverse position. I'm sorry, Professor, we cannot hear you. Not yet, Professor. we still cannot hear you, Professor. Sorry.
Hello.
Now, yeah, we can hear you, sir.
Okay. Sorry. Okay, sorry, Mr. Chairperson, Mr. Fadli. Can I start now?
Yes, you can start now.
Okay, thank you very much. Assalamualaikum and very good morning to all. Thank you for the problem just now. Okay, for this session, okay, for this invited speaker for inorganic part and material chemistry as well, we are very lucky today as we have our very respected presenter with us today. I would like to introduce that our next invited speaker will be Professor Yang Gun Ko from Yunnan University. Okay, Professor Yang Gun Ko completed his PhD study from Pohang University of Science and Technology in 2006, and then continue his postdoc as well in the same institution. And then after that, in 2007 till 2008, Professor Yang completed his postdoctoral in MIT, Massachusetts Institute of Technology, in Department of Material Science and Engineering. In 2009, Professor Yang started his career in Yunnan University in School of Material Science and Engineering. So, so far, for the quick introduction from Professor Yang, he has published around 182 publications, with about 137 as a corresponding author. And then Professor Yang as well, being the editorial director for Korean Society for Technology of Plasticity, and as well as the editorial board for Metals and Materials International. Okay, I think we are very lucky today for having Professor Yang with us, and I wish that Professor Yang will share with us his research as well as his current findings. So I would like to leave without further ado to give the opportunity to Professor Yang to continue his presentation. Thank you very much.
Hello everyone, my name is Professor Yang Gong-go, Yunnan University, South Korea. This presentation has the two graduate students who graduate from UGM School, Lucy and Ellie. Say hello to the audience. The topic I want to talk about today, advanced surface modification using plasma electrolysis for better properties. Before starting this presentation, let me introduce myself in the laboratory first. I just graduated from the postdoc, and then I just moved to United States and MIT, working at the postdoc research for 2 years. And then after that, I became the professor in Yongnam University since 29. And there are several paper publications. My H index for your convenience, for your understanding is in 36, and then I hope that this number will increase very soon. And this year, this laboratory was selected as National Research Laboratory. It's pretty honorable. And then the other aspect, and then the Yongnam universities. From the map, the case, and then you can find Indonesia right here. Yogyakarta Museum in this place, and then South Korea right here. In approximately 8 hours by airplanes. Yongnam is located in the third largest city in South Korea, Daegu, and you can find the several photos. Spring, this campus become very beautiful with the cherry blossoms surrounding the whole campus in the summer, the fall, and the winters. Winter the case in there we have some kind of snow. That's why and you can experience this kind of snow because I just think that this is an unexpected experience. And my research laboratory just like this and that, consisting of the really many researchers from the all over the world. Indonesia, yeah, surely right. In Turkey, China, Morocco, Syria, and South Korea. That's why and that we are really work hard to be the world-class level laboratories. The first chapter is introduction, and then main motivation of this research work is twofold. First one, and then metal have two different inherent disadvantages. First one is high density. So that's why we need to increase strength and ductility. This is the mechanical part. The other aspect you may interest in, and also I just working for right now, is the enhancements of the surface property. Yes, protective subcoating layers. So only material case and the metallic material shows some kind of poor corrosion resistance, and then some methods will be combined to enhance the corrosion properties. Among the process, and then plasma related oxidation, yes, British scientist Ashley Yorkins, and then he discovered the importance of the process method. Simply, I will explain that this is simple wet coating analysis. Anode and then cathode oxidation reduction happen once we just give some kind of electricity to this kind of system, and then there's some kind of electrochemical reaction. Left side and right side, and then voltage time decay, and you can find some kind of flow curve. And then there's some kind of curve shift will be changed point of the breakdown voltage. Over these kind of voltages, we can call this plasma related oxidation. And then during plasma process, you can find the plasma spot.
Professor,
Yes,
may I
Ellie.
ask some question? What is the parameter in the PEO process?
That's a very good question. And then to be a good scientist, even independent, first of all, you must study what is the main variable in the process itself. So I can summarize the three-fold approaches. And then, yeah, surely we have to consider substrate itself. The other one is wet coating process. That's why, and then we must study electrolyte. And also, in-down electricity into the system. Yes, surely you must supposed to study current condition. It's about electrical parameters in them. So several any details. But this laboratory is focused on what kind of effect is coming from the electrolyte, the formation of microstructure and properties. Those are electrolytic agents and passivating agents and complex agents and insoluble agents. And then, broad sense of the chemistries, and then we have the 4 different ideas: soluble, insoluble, and then inorganic, organic case, and then any kind of connection, we can tailor the electrolyte to form specific coating structures in them. Understand that? Yes, there are many, tons of research works in them nowadays. So-called ICCS paper publication. Even now, you can give a keyword of the PO into Science Direct or Web of Science. You can find so many papers. Even some scientists study and report this data into SCCI. But I strongly encourage you. This is our current paper published in Progress in Material Science, whose impact factor is approximately 40. In comparison to the Nature and Science, really is top journal in the world, and this journal is very so close. This review paper, and it's a big honor for this library to gain this kind of opportunities. So if you are really interested some surface modification using plasmatic chemistry, please read this one. So our scope is very simple. As I talked before, and then there are 4 different metallic materials, so-called valve groups, and then aluminum, magnesium, titanium, or even zirconium. But here the case, and then for the fundamental, some kind of performances, and how to control the surface structure for better functional properties, or some also can we design some new novel pure processes. So this presentation hopefully they contain oral presentation, but because of the limitation in the time, that's why. And then in case I will try my best to deliver my whole presentation. Experiment apparatus, and then we use several machines, and then we have several instruments to observe the microstructure or characterize composition, and then those are the all kind of concepts. And then for the chemical approaches, and then polarization analysis and impedance analysis, this is pretty backbone. How can we just understand the electrochemical behavior, and that's connected with corrosion behavior. Sometimes we just use equivalent circuit model to quantify the load of each layers, the formation of corrosion behaviors during the corrosion testing. The first result is short is about the fundamental. I have 5 different ideas. First of all, I just said before in the plasma electrolysis, plasma electrolyzation, where the plasma spark will be the predominant mechanism to form some kind of inorganic layer on top of metallic material. That's why here we must know the plasma itself. It's very high temperature, but no one knows how hot it is. That's why we have to measure directly or indirectly. The other one is soft plasma, and then electrophoresis, and then evolution of critical analysis or controllable plasma discharges. And then there are 5 expanded research work, and those are all published into several good journals. First topic is the temperature of the plasma spark itself. Top scientist, one of the top scientists in this area, Hussein, and he just mark up and they measure the temperatures. Those are temperatures roughly 5,000 up to 10,000. The wide range. That's why this kind of temperature is not so clear, because there are some kind of limitation. And then here, professor want to handle the temperature estimation by utilizing incorporation. This concept is very simple. Do you know the crystal structures? Crystal structure change will be valid depending on the temperature to be exposed there. This is temperature, and then we just use titanium oxide, zirconium oxide, titanium and zirconium respectively inside the coating layers, and then from the temperatures to show some kind of phase transformation, the crystal structure changes, and then I hope that we can, in direct manners, and that we can measure the temperatures from 2 different oxide material. So these are TM images, and then from the spark patterns, and then we came to know the crystal structure. And then this one's convinced by the XRD patterns. And then PiO2 still remain as a tetragonal structure, and then zirconium decays, and then about apart from the cubic structure. So that's why we can summarize in them. Maybe the plasma temperature in this condition, hopefully this condition will be universal and I just think, and then around 2002, 1500 the Kelvin, and then around this temperature. CNT, the carbon nanotube can be incorporated into the oxide layer during PO process to enhance functional properties. And then how can you incorporate this one? If you take off the schematic illustration and then electrophoresis means where some kind of substance is dispersed in the electrolyte, having some kind of shooting effect, positive or negatively charged ions, and then this should be migrate toward anode or cathode. In this case, migrate toward the cathode areas. And then local diffusion should be incorporated inside the inorganic layers, and then it should be functional. The other approach is, and then what about the substrate effect? And then some metallic materials show some kind alpha and beta different phase. So each phase have different electrical conductivity in them. So from the time voltage curve, we can see some kind of double breakdown phenomenon. This is highly rely on the formation of the different phase structure with the different electrical parameters in them. So we just simulate and show some kind of schematic illustration in them. Effect of, as an effect of substrate and then grain size. Grain size is very important. One grain size and a small grain size. Big grain size that case in the less grain bound area. Small grain size, even nanocrystalline structures in them. It's just decorated by so many, much of regions with the interface area. This interface area, the property will be totally changing, totally different from the grain bound itself. That's why, and then by calculating this grain modification, and then we can see different behavior, morphological behavior in terms of nucleation and growth of the inorganic layers. Surely, and then crystal structure. Sometimes, this is a high temperature. Also, newly formed oxide layers in contact to cool electrolyte and then quenching will be applied. That's why some structure should be the amorphous structure without no grain boundaries. So those are simulated, and then we just observe some kind of behaviors in there. Inner and outer layers show some kind of different aspect.
Sir.
Yes. Rosie?
Among PO mechanism, could you explain more about soft plasma?
Yes. Actually, I just missed one point in there. Soft plasma. This is a very new concept. Okay, this is also very new and very difficult. That's why I want to give some kind of example to compare each other. Volcano, the plasma electric oxidation. Volcanic activities, plasma oxidation is almost identical. Yeah, there must be the advantage, good disadvantage. But if you take a look at this kind of pictures, the volcanic activities, there's some kind of pore and new formation of island or some other things such as Hawaii or Jeju Island or some island in Indonesia. Like this one in the plasma characterization, that you can see some kind of small, the red or yellow one. This one is small volcanic activities. Then we can control this dispersion and size and intensity, even color as well. And then the final formation of surface area almost identical. Matter is in them. Big volcanic activity like Broma mountains. You can see some kind of huge craters in them. Huge craters, okay, you can apply this kind of concept into the metallic material that gets in them. It's pretty noxious for the corrosion properties. That's why, and then I want to really control the size of the plasma spark. Sometimes I want to give us some hard energy, sometimes I just get soft energy. Soft case, and then yes, I can call this soft plasma. This is new concept from this laboratory for the first time in the world. So if you take a look at this kind of photos in there, these are plasma spectrum images, and then this is general. You can see some kind of bigger plasma spark size in there. This side and then this color change into significantly and then reduce in its size significantly. And then there's some kind of additive, copper additive, ethylene diamine tetraacid. This one is hollow structure. hollow structure, in that case, and then we can add some kind of special material, copper or the other some kind of metal ions in inside, and then this kind of structure can generate the specific reaction during the pure process, and then we observe. We also found that the role of this kind of EDTA special agent to reduce the size of the plasma spark, and then I can convince the many scientists that we can control successfully the size of plasma spark. So that's why small size, there should be a soft plasma. And then now go for some kind of interesting properties in that. If you take a look at these images, it's a case of a mobile phone. Gray, yellow, red, some kind of olive colors, black or purple, any other colors in them. Striking point, even strong advantages is coming from plasma electrode oxidation itself is to change the color of the structure in them. This one is simply for aesthetic purpose, or also we can put in some kind of desirable properties. Why? This should be vanadium oxide and tungsten oxide. This is also kind of functional property. So not only color, but also some kind of specific property will be expected at the same time. And then dye-synthesized solar cell. And sometimes we just tailor the surface structure of inorganic layers. It should be pillar-like structure. Yeah, this is not pure process, but this is cardinal pure in the anodizing method. And then this kind of pillar structure is very uniformly formed. It's throughout the whole structure. And then we can fit in some kind of special functional material or increase surface area. And then after that, after this kind of concept, and then the dye-synthesized solar cell, the efficiency level is above 5%. This one is the really ancient research work. I hope that this number will be increased double. Implants. And you know that many people, once they just lose their teeth and then for their some kind of enjoy of life, and then new implant system should be implanted. So this is the highlighted value. Here I want to put forward two different strategies using the plasma electrolysis. First one is simple pure strategies. The other one is how can we form pure hydroxapatites that is on form of the titanium substrate. And then those are the very, very creative ideas. And first one, and then yes, and then with an aid of the phosphate electrolyte, and then we can change it, the surface structure. Sometimes we just use sodium phosphate and silicate that case, and the formation of a surface structure looks like a pillar structure. It's not irregular anymore. That's why also the urgent strength of this newly formed oxide layer is not stable enough. That's why it's not a case for the biomedical approaches in there. So we just control the surface structure by utilizing potassium phosphate in there. But there are two different phosphate, K4P2O7, K3PO4. Each potassium electrolyte, it can change its surface structure. And then if you take a look at the K3PO4, K4P2O7 the case, and then it looks like the soft and hard plasma electrolysis. And then so this is more about the biomedical properties, and then the formation of hydroxapatites during acid-base solution. This one is very rapid. So that's why we can conclude K4P2O7 3D desirable titanium alloys with the better formation of the inorganic structures. What about the zirconium oxide? As I described in the previous section, and then the incorporation of some particle or incorporate some substances either chemical and physical way. This is a physical way, and then zirconium oxide will be incorporated into titanium oxide by electrophoretic activities. So this is the result, and you can see some kind of pore together with some white substances. Those all turn out to be the zirconium oxide. Very, very uniform, and then it's very good for formation of biomedical apatites. This is another data, and then can you see some kind of cell structures? Once this is the mouse cell, and then once we just insert some kind of small mouse cell on top of our desired material case, and then this cell will be anchoring first down connected with some micropore, and then this should be proliferating then. And then its size and its number. So from these approaches and then incorporation of with the zirconium oxide into the titanium is the best combination. So that's why we can propose is the the composite material to trigger the formation of the cell structure. And then what about the bacteria? Cell and bacteria, those are almost identical. But the cell is the desirable, but bacteria is not good. That's why, and then we have to take the cell, but disobey the formation of the bacteria. Sometimes AG is pretty the favorable effect coming from this cell, and then we can kill the bacteria very effectively, not killing cell anymore. These are new types of implant system. And then what about that? The previous approach is in titanium oxide, bimetal apartheid. There is some kind of multi-layer concept. Even by apartheid case, and then cell will be anchoring on top of the surface structure. But here we just omit oral process, and then metal and then hydroxyapatite. This was surely new concept, and then we use the electronic porosity deposition method. Even this kind of case, and then first of all, this one is pretty uniform, and then crystallinity also is desirable. That's why, and then the final formation hydroxyapatites happen very, very rapidly. That's why, and then we can suggest this kind of research work to electrochemical maybe 6 years ago, and then also this one, several companies in South Korea are interested in this technology. This is almost last section, and then what about it? Can we learn something from our mother natures? Yeah, this is my first concept, because evolution is very, very long history. We can get a good lesson from it. So this is the flower structure. You know, artificially, we succeed to fabricate these kind of structures very, very successfully. You know that, first of all, this one is very uniform and then very homogeneous. Considering the concept and then the higher surface area, and the more the functional property will be expected. That's why, and then imagine this kind of structure show the enlarged surface area and then provide some kind of property, surface-driven properties such as biomedical or solar cell effect or some kind of catalytic formation in there. So yeah, surely we just use this kind of approach using the sample assembly, and then we just study, even discover the fundamental approaches of this kind of nature-inspired architecture structure, and then by using plasma electrolysis. Yeah, those are all my presentation, and then thank you for your concentrate on this kind of presentation, your interest. And this one shows the whole image summary of this research works, and then volcano, flower image, plasma stack, and the circuit model, and biomedical approaches, and then as a background of the Yeongnam University. Thank you again. Goodbye.
Okay, thank you very much, Professor Yang Gun-ko, for nice and attractive presentation. It's a very good one. So we have a few questions in the chat box, but before that, I want to ask the first question. So, Chairperson, I think it's good for me to ask the first question. Prof. Yang, I mean, one of the slides for your result discussion, you show that how the PEO is bonded together, is embedded together with the EDTA. And we know that EDTA is the good chelating ligand. I can understand how PEO and embed together with copper EDTA, but in PEO and EDTA only, how you can propose these two is embed together?
Embed together. So, okay, your question is about the advantage coming from the EDTA in the electrolyte case, and then this one is not universal. It's pretty specific case, and then once EDTA
This one is melt down inside the solutions, and then we just give some kind of electromagnetic first inside this structure, and then irritate it just show some kind of catalytic activity to trigger electrochemical reaction.
Okay.
But the more striking point, and then irritate, it has some kind of hollow structure, and we just put some kind of metallic material inside in there, such as copper, Fe, some transition metals. And then the dramatic point, and then irritate itself decrease the size of plasma spark. And in addition to this one, and then copper inside irritate just migrate toward the anode structures, and then copper move out and then react with the oxygen to form copper oxide, and then that's why sometimes this concept can be used for the smartphone decor, and then we want to make some kind of black surface layer in the case, and then copper oxide in the case, and then looks some kind of dark brown. That's why by using the two different approaches, that we can fabricate some kind of highly compact some oxide layer together with some kind of specific color for women. So, am I correct? And then, my answer is close to your question?
Yeah. It's, but further than that, what is the difference between if you use copper and without copper in EDTA?
It colors.
The colors.
In fact, in the color itself, and then without not using any kind of the metallic material inside the case, and then we cannot take some kind of advantage coming from the incorporation of metallic oxide. EDTA the case, and there's no. So EDTA just stay there, and then this one is not decomposed, and then not working as electrochemical. It just trigger the formation, and then the copper EDTA almost identical, but copper move out to form some kind of dark brown color. So that's why main disadvantage is, difference is the color.
Okay, good. If we choose another metal, maybe the color will change as well.
Yeah, sure. And then, so Ellie, can you show some kind of presentation files, and then the slide, and then the color image. Yes, if you take a look at, and then this one is shown, right? Right. So if you take a look at these left side images, and there's some kind of gray colors, yellow color, red ivories, and then black colors in there. So this kind of is coming from the tailoring some kind of electrolyte system in there.
Okay, great. Okay, we have one question in the chat box. Okay, the question from Indriana Kartini. How does zinc oxide or titanium dioxide resulted in higher efficiency for the SSC compared to titanium dioxide? It is due to the nanotube structure of band gap engineering. You have any?
Yes, and then the slide, and then this slide and this one. Maybe this slide, and then only titanium oxide case, and there's some kind of limitation in band gap energy. So from the band gap engineering the case, and then once we just doping some kind of pure material doping with some kind of the other, or such as zinc oxide or different types of oxide structure, and then the case, and then just intermingle each other, and then we can reduce or sometimes increase the value of a band gap. And this band gap also pack the photo converting the effect. That's what, and then here we just summarize. Can we summarize some effect of the additional incorporation material? No, not this one, this one.
Okay.
Yeah.
Thanks.
Yeah, this one, yes.
Okay. Are there any question for others, audience, from the audience? I just want to know one more. How you do this experiment? You have heated your sample or maybe your product until up to 11 Kelvin.
No.
Sorry, 11,000 Kelvin. How you do that actually?
Okay. The point is, and then main mechanisms to form the oxidal layer by using plasma electrolysis is high temperature and high energy status in them. So previous research work, this is a previous research work and done by Hussein and one of the top scientists in this area. They really want to know the temperatures. Maybe this one will change some kind of surface structure and trigger some kind of electrochemical formation in it. They try to measure the temperature in that way. Okay. And then those are around this level, like a volcanic activity. But this temperature is very wide. So here the case, and then by using some kind of transformation, different oxide materials, and then we just expect that there must be a pathway to measure indirectly then the plasma temperature. Here, and then we just use some kind of phase transformation, crystal structures, and then we confer. It is infer that case, and then this system, and then plasma temperature 2,500. This is just kind of just normal case. I never artificially increase the temperature. This is just a normal by the electrochemical simple reaction.
Okay. Thank you very much, Professor
Thank
Yang
you.
from Yongnam
Thank you,
University.
Chairman.
I very enjoyed to watch your very attractive
It's my pleasure.
Okay. I think that's it. I think we have the
Right.
time. Okay, thank you again, and then welcome. Yeah, thank you very much for your presentation today. Okay.
Thanks
Okay,
again.
so I give back to the Mr. Fadli and as well the organizing committee. Thank you very much.
Thank you, Professor Young Gunko, for the great
Thank you.
presentation.
Thanks so much, Chairman.
And thank you, Dr. Riza Razali, as the moderator. Ladies and gentlemen, for the next session, we are going to have a parallel sessions. After the end of the parallel session, we are going to have lunch and prayer break. Then the fourth keynote speech will promptly start at 1 p.m. Western Indonesia time. So please go back to the main room 5 minutes before that. For those who joined the parallel session, it will start immediately. And now you can proceed to your presentation room. Thank you.
Assalamualaikum. Ya baik deh, saya udah terima. Nanti di-share ya.
Good afternoon, ladies and gentlemen. Welcome back to the meeting. Now we are continuing to our program. The next program is the fourth keynote speech that will be delivered by Professor Pranut Potiaraj, PhD, from the Department of Material Science, Faculty of Science, Chulalongkorn University, Thailand. In this session, the keynote speech will be moderated by Professor Dr. Karna Wijaya. Now, please welcome Professor Dr. Karna Wijaya.
Ayo, good afternoon. Assalamualaikum.
Waalaikumsalam.
Sorry Mas, ininya agak kurang stabil ininya internet di sini.
Baik, Pak.
Oke, sudah bisa kita mulai?
Sudah, Pak.
Oke ya. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Everyone, thank you all for coming ya. Could I have your attention please? Let me introduce my name Karna Wijaya. I'm from Department of Chemistry, Gadjah Mada University, and today I'm the chairman of the session. So we are pleased to welcome Professor Pranut Potiaraj, ya, a very special guest ya, from Chulalongkorn University, Thailand. And Professor Pranut Potiaraj's specialty is material science, and he is a director of metallurgy and material science research institute, Chulalongkorn University, and many other professional and administrative position. And today, Prof. Potiaraj will be sharing with us his expert opinion on smart textile as wearable sensors. Okay. I ask that you give your full attention to Professor Pranut Potiaraj and help me in welcoming him to the stage. Okay, Professor Pranut Potiaraj, please your time, 30 minutes for presentation and 10 minutes for asking question.
Thank you very much, Professor.
Yeah.
So let me share your. Okay, so thank you very much for asking me to give the presentation today. So I have read through the programs, and it is a very interesting conference. I know that in the COVID outbreak situation, it's quite difficult to manage academic event, but I think we are getting used to that now. So. I think in the next half an hour, I would like to talk and discuss with you about the use of the textile in the new field or in the new application, apart from the conventional, and maybe you quite similar to this word as the smart textiles. But smart textiles can be in various forms, but the things that we're going to talk today will be about the wearable sensor, which also one of the most interesting field nowadays. First, I would like to reintroduce myself again. Right? Actually, I'm from Chulalongkorn University, so I work for two places. One is the Department of Material Science, Faculty of Science, and also now I'm the director of the Metallurgy and Material Science Research Institute, which is situated in Chulalongkorn University as well. So, but actually my background when I graduated is from Manchester. Like you may know, in England there are two big universities that teaching in textiles. One is the Manchester, the other one is in Leeds. That the two that have quite strong in textile fields in the past. So after that, when I come back to the university, I'm teaching in the Department of Material Science, and I think my research work has evolved from conventional textile. In my PhD days, I dealing with weaving of the things, even using the computer with the weaving. But just after a few years, I think if I still conducting research on weaving, there are no student will working with me anymore. So we are gearing towards a new application of textiles. So in this slide, I would like to show that textiles used to be one of the most important exporting business back in Thailand, like 20 years back or more than that, right? I think many countries in Southeast Asia, including Indonesia, have to have this export business as a big business, and used to be one of the most the highest income for Thailand. But many factors has made this the conventional export of the conventional textiles and garments it's declining for many continuous years. So if we have a look, there are many factors like in last 20 years, we talking about our labor cost, which is higher. So we couldn't compete well in the market. And in the field, years back, we got the pandemic or even the global economic activity. So the normal textile business is quite declined. So it's the policy of the Thai government to try to change this textile business back to a good shape again. But they have to do that because we used to have the workforce in the textile industry for like more than a million people in the workforce. So you cannot just sit and see this industry collapse. So this industry try to adapt themselves. We try to make the value-added textiles. We gain through the more general terms of this one. We call it technical textiles. Right? Yeah, but in technical textile is broad. In technical textile, you also mean the automobile textiles, the high performance composite materials, things like that. So in lately, so we focus more on things called smart textiles. So not only in Thailand that the trend of the smart textiles it's emerging, as I think the lifestyle of people is changing. So many forecasts that smart textile will account for income in the textile sector. So if we look at the global smart textile market by application, I think we can see that the last increasing we find the healthcare application. As you may know, the aging society is coming is a problem of the globe, the world now. So I think people would like to take care of themselves, take care of their family. So the healthcare business growing very well, and the smart textile has been one of the main factors in the healthcare business as well. But if we look through the other angle of the function, what the smart textile market feel in this function, right? They are increasing in many applications, right? For example, in energy harvesting, right? Very important field as well. But another important field is the sensor. So I think our focus at our lab, in my research lab, is trying to going to the direction that the application of our research can be used in real market. So we focus on the sensors application as well as in the healthcare application. So the smart textiles now they are the other broadened word. We call it just variable sensor. Variable is maybe a bit broader than the word textile, but it's the thing that you can wear, right? So it may be not in the form of clothing, but maybe in the form of like watch, belt, hat, and everything you can wear is called wearable. And wearable device is coming near to you. So I think many of you will have like smartwatch. That thing is like a wearable device as well. And I think this kind of device is getting more and more and more. In this device, one of the main factor is the sensor. Sensor is very effective because it can directly patch, because we want to measure things on our body, right? So we can collect the important information from our body. If you have like Apple Watch, you can see that they can or other smartwatch, they use the light technique to measure some bio data from your body. But we also can take the human fluids from our body, like sweat, because we have sweat when we doing activities, or we are playing sports, or in tears, or in saliva. I think we are getting used to this thing after the pandemic, because we use this thing to test for with infection anyway. So the advantage of using this thing is that we can integrate that things into our clothes. So there are many factors, many components that need to be developed, right? We have to develop sensor, of course. On the other hand, we are going to develop also the energy storage device. So I don't think nobody would like to carry a battery, a big battery which is heavy, or battery which is quite rigid. So in that field, it's quite important as well when you go for a device. Another technology that involved is the IoT with IoT technology, because now we would like to have the real time or continuous monitoring to help us to have the better lifestyle. So if we look to one man, we can take this variable sensor into many aspects, right? We have like socks and shoes that can count your actual walk, and we can have the like headphone, or we can have like smart contact lens that can adjust for the lightness of the day, things like that. It's quite close to our lifestyle nowadays. So it was predicted that the trend will be increased. It is already increased in this time that we get a lot of wearable sensor, and also we predict that it's still going to be a good business. So it's changed from on-site diagnostic screen to the wearable sensors, right? When we have the lockdown, we cannot go out of our home, and we like to have the doctor to see our live signal, things like that. Wearable sensor will be in the use and very useful in this situation. Like I said, the aging population is the things that making the health monitoring, and in the future. In the past, in I think in Southeast Asia, there's no problem because we are a big family, so we have people to look after the older age. But now I think our lifestyle is changing. People have the smaller family, but we still have our parents to take care of. So this variable sensor would be very useful in monitoring and help take care of these people as well. So what is the main application of variable sensor in healthcare? So application like chronic illness, or we wear sport watch to be like wellness monitoring, and we also have like sensor therapeutics when the drugs can be given to you when needed, things like that. So there's a lot of application. One of the application is the chronic illness and at-risk monitoring, which for some disease is very important. So in people try to use one of the textile products to use as a sensor. So we have the sensor in many forms as a substrate, like polymer, like paper-based, or even textile. What is good about the textile, especially people use the thread as the substrate for the sensor, is one of the main advantage is we need very low volume of reagent and sample. Reagent in the sensor field, even especially in the biological sensor, is quite cheap. So if we can use lower amount of this reagent, it will be good. Also, the low volume of the sample collect from your body is quite important. We just need to collect at least sample from your body, right? The second one is in the thread. They have the property that is like is promoting the self microfluidic phenomena. So the sample, the collecting sample will go to the sensor area quite easily. And the other is when we use this one, the textile as a sensor, we got the normal comfortability for textiles, and most of them is biocompatibility. When I'm talking about biocompatibility, it means like from outside the body as well as inside the body in some application as well. And these materials can be available at quite a low cost. So our research related to variable sensor, we do both in the fabric one and the textiles one. For the fabric, which we will go deep a little bit later, is we develop the calorimetric sensor to detect pH from sweat, also lactate from the sweat. For the thread sensor, we developing both calorimetric sensor for glucose monitoring and urea. So why these four things that is on our focus? Because we first focus our products, the end product or final goals products for aging people. So for the aging people, we have a lot of problems with the disease. Like in one of the most problem, we have a lot of disease in our aging people, like Alzheimer, heart attack, respiratory disease, or cancer, or diabetes. So if you are diabetes, what things that you want to do is to check your glucose regularly. And the most popular device that people use nowadays is to use the small needle to detect the glucose from your blood, right? But I mean, if you have got diabetes, you know that when you have some wound on your skin, it's not so good. Even very small wound. And people that have to do the glucose test regularly, you have a bit some pain. This is for aging people. Our group also talking to the pediatric for children. I think they have some trouble as well, because if the children who have the diabetes, they have to collect the blood as well. So we would like to use this wearable sensor as a non-invasive fashion, that So we are not going to take the blood from the body. So actually, we have research that detecting biomarkers in the blood as well, right? That one is that's why we focus on glucose. Also, we focus on the lactate level in the muscle. At first, we target on the active aging groups. You can see that in the park, there's a lot of aging people looking for exercise. It's look good, but I mean sometimes it's quite risky because you never know that they will have a bad condition on their health or not during the day. So people the sweat of the people we're going to have the muscle fatigue will contain a lot of lactate. So we try to measure the lactate to prevent people from have the muscle fatigue during exercise as well. So lactate can used to detect what another call is the diabetic ketoacidosis. Is a complication occurring when glucose is high for too long. So we also, apart from glucose, we also able to measure the lactate as well. So this is the problem with the blood drawing from our body. So apart from making the sensor can wear easily, smaller, more efficiency, can we also transform from invasive to non-invasive diagnosis as well. So variable chemical sensors directly patch onto human skin and clothes to collect information from human fluids are developed in our case. So what is the easy fluid that can take from your body is sweat. Sweat is colorless biological fluid with like slightly acidic in the range of a bit acidic. Because this sweat can have a lot of biomarkers in them, like electrolytes, metabolites, small molecules, as also the proteins. So if we can measure the amount of this one from the sweat, it can be used to monitor the health as well. So in terms of detection techniques, one of the technique we use is the colorimetric sensor. So when it's like the pH meter. When you put on your sweat or your sample, it's changed color. This is called colorimetric sensor. The advantage of the colorimetric sensor is you don't have any other device to read the result because it's easy to use and it's quite inexpensive. But anyway, because you have to look it by your naked eyes, so it's maybe sometimes it's misleading when you interpret the result from the sensor. A bit more on the higher cost one is electrochemical sensor. If you use electrochemical sensor, you can measure things in more precise way, but you need to have the equipment to read on your data, like potential stat, and then convert to electricity. What good thing that you can precisely measure the biomarkers. They have higher selectivity and rapid, but nowadays I think we can get the smaller potential meter. So or you can have like things like this attached to your mobile phone, and you can use to measure things. Also, our group use if we use both of the technique, we cooperate with people from national electronics and technology center or NECTEC to develop the readout mechanism that can read out the result and send the result to your mobile phone by Bluetooth or by Wi-Fi. So this one is in the future that we can use to monitor the health of the people who wear these things. So we have many designs, like we have the watch look like smartwatch, which we can measure glucose and lactate using the colorimetric sensor, and we use the circuit, the electronic circuit, to read these colors and then show it as a number. Or sometimes if you are using this device in the quite an older people, they not have activities to have a lot of sweat on your wrist, we can have the measure on your waist as well. And this one, because on the waist is difficult to see, we can send the readout back to the mobile. Right? Okay. So this one is our research. It's a textile-based colorimetric sensor for sweat, pH, and lactate detection, and thread-based. This is original design as the fabric. It's quite good, but things that we have the trouble as we have to use a lot of reagent when we use the fabric. So in the second design, we changed from the fabric to thread, and we found that we use lower amount of the reagent, but we still can see the change in color. This is just two textile-based variable chemical sensor that we also use. The other technique we use, we call the using the length of the color change. If you can see, this thread not only have the change in color, but they have the length in change as well. So instead of seeing the color, we seeing the length that the change had happened. If the length changed a lot, which means you have a lot of biomarkers chemicals in our measurement. Right. This is the technique. These two techniques can use under naked eyes. From this fabric, we also construct a readout. This is a picture from the real machine that we can use the readout, which we can read the pH and lactate from our sweat. And now we are in the stage of clinical trial in the we got it patent and we got it on the contest, but anyway, because there are no contests outside the country for few years, so we didn't put this one to go for the contest. But anyway, we can measure this value from the sweat, and we are doing larger amount of clinical tests now because it is kind of medical device, so you have to register with the authority before you can take this as a commercial products. So the concept behind the non-invasive textile-based colorimetric sensor is to use the enzymatic-based colorimetric reaction. So we loaded some enzyme which can react with the biomarkers and then give the products that have the color. So this is roughly the concept that we use. So it can change color depend on the amount of the biomarker we use, because if you have different amount, it reacts with the enzyme in the give a different color. So after that, we changed from fabric to thread one, and we also try to modify it to have quite a good sensing. We also use graphene in the form of graphene oxide to help that to increase the gain, increase the sensitivity of our sensor as well. Right? So now our device can detect the glucose on the range between 0.06 to 0.011 millimolar, while the abnormal one is around 0.3, right? So, but urea we also we can detect as well from your sweat. This one is the the papers from our work. And so when you're doing things with this one, even if it's on your watch, we change the design from the without like this to the watch. So we have to go for clinical test. This is a test to say that is our sensor have effect on the human skin or not. So we have to do the clinical safety as well. So this one we use the thread. Change from fabric to thread, as I told you, to reduce the number of these kind of enzyme and catalyst, which is quite expensive. So we success that we change from fabric to the thread. One of the good thing about the thread, like I told you before, is can suck the fabric up to the material is quite fast. So we taking two, we construct two sensor. This sensor is made from cotton thread, and then we coated with the absorber, the enzyme absorber, and also the assay, the glucose calorimetric assay. The other side, we have the working electrode to measure the things by making them like with the conductive ink, and then we have the readout. And in the watch, this is the real watch we construct from our sensor. So this is we are trying to use the electrochemical thread, which can detect things in more precise way. But anyway, we have to we are in the progress of making this one, making the watch to be a smaller one. This one is like I told you, another technique that we use the intensity or the length of the.
I'm sorry, Prof. Putieraj. Actually, but you can continue. Yeah.
Okay. I think we're going to finish in a few minutes. All right. Okay. So we use the length as well. So to get this one published, or you can in the journal as well. So this is roughly all the work we have developed, and the team that we developed this one, and we are in the progress of making in the real device that can be on the market. But anyway, it's taking long time, because after we develop, one of our drawback is we didn't talk to the doctor before. So when we go talk to the doctor, there are more and more requirements. So we have to go back and modify our work as well. So now we are working closely with the doctor teams at the university hospital to make this thing can be used in their work. Okay, thank you very much, Professor, and the audience.
Okay, thank you very much, Professor Putieraj. It's very interesting presentation. Yeah. Okay, ladies and gentlemen, and now come to the question and answer session. Yeah, please, yeah, we from audience, you can ask directly or use the raise hand feature in Zoom. Yeah, then unmute your microphone, please. Any question?
There's one question in the chat, Pak Ana.
Yeah, okay. Okay, I have a question. Ada di chat. Sorry. Okay, sorry. Okay, ada question dari Bu Indriana Kartini ya. Thanks for the inspiring presentation. Yeah, so far, has the smart clothes been in the market or still in the lab? Yeah, it seemed to.
I saw a lot of smart clothes is now on the market.
Okay.
Maybe now in quite what to say, specific groups, like the one who have the like marathon athletes, they try to have the device that can monitor, because it's quite risky for marathon runner, things like that, or the trekking people. So that one is quite specific. So the price maybe not now it's not available to broad group of people. But I think if because of the textile and the technology, we trying to use things in cheaper. So we try to make the device available to more and more people. Like I think if we produce it in a large scale, like now our watch, because we have to go produce one by one. It's quite expensive. We use a 3D printer, so in terms of industrial, you get cheaper. Or even we send this one to do the prototyping in China, and yeah, do things very good. I mean, if you want to go for prototyping in China, it's quite good place to go. And we have quite a good, like very nice watch. But I think if we are going to make it available to people, I think we have to deal with the large amount of the production technique as well.
Okay. Are there any question more, please, the audience? Okay, I have a question, Prof. In addition to being smart, currently green textile is also growing, and I think it's becoming a demand. What do you think about the prospect of this smart and green textile in the future? Is there maybe possibility that this aspect are developed in the textile?
So I think like I told in the slide, that we target to use these smart textiles on the one of the group that we are focusing is on the aging. When you're talking for the aging people, there are two groups. One is the aging. You are old, but you can still doing activities. But who is the group that on to stay on the bed, things like that. And we have more and more of this group. And like I think we share the same culture, that we have to take care of this our parents and things like that. So but your lifestyle, you have to go for works and things, and cannot have like people to look after them all the time. So I think that one will be a good chance for these products to be launched. That the first one. The other group, like I said, is the athletes, because in the younger generation, people be aware much on their health. So I think they're going to want to know that their health is in the good condition or not.
Okay, thank you. We have
the
question.
question.
The reproducibility, long-term use of the textile sensors.
Okay. That one, if you see from our sensor, now it's still the off, used as the one-off things. So when you measure, you have to change, like you have the blood glucose one, you have to have one needle, and when you have the data, you just throw it away. But we are the process of developing, reusing, that you don't have to take it off. But now our technology, we still have to take it off after one measurement, and then taking the new ones. But what we know the problem after we go to the doctors, that they would like to have like continuous monitoring, that measure all the day, measure in the morning, measure in the evening, and then send the signal to the doctors or the caretakers, so they can know the status of the patients all the time. So that one we try to measure the reproducibility or reuse or the long-term use of the sensors.
Okay, any question more? Yeah, we have 1 minute left. Yeah, I think this is not enough.
Okay.
Okay, thank you very much. Yeah.
Thank you.
Okay, ladies and gentlemen, I think we finally come to the end, of the plenary session. Before I close this plenary session, I would like to take a short conclusion. That the combination of textile and sensor have led to the development new capabilities. fabrication with potential change how the consumer interact with the clothes and other textile products. I think maybe such conclusion. Okay, closing I think finally, I would like to thank to Professor for the informative interesting presentation on all participants and very active. We have 3 questions Okay, finally let us give the applause to the speaker and thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Professor. Everybody.
You're welcome, sir.
Thank you, Professor Pranut Potiaraj, PhD, for the great presentations. And thank you for Professor Dr. Karna Wijaya as the moderator. Ladies and gentlemen, there are a few sponsors which support this event. One of them is PT Ditek Jaya. And this is the introductions video of PT Ditek Jaya. Please enjoy.
Excellence in Science, Shimazu. Excellence in Science, Shimazu.
Ladies and gentlemen, now we are continuing to our meeting. The next program that is to hear the fourth invited speech. This speech will be delivered by Dr. Bambang Purwono, MSc, from Department of Chemistry, Faculty of Mathematics and Natural Sciences, Universitas Gadjah Mada, Indonesia. In the session, the invited speakers will be moderated by Dr. Mardiana Said of University Science Malaysia. Excellencies and all participants, please welcome Dr. Mardiana Said.
Thank you, Mr. Fadli. You can hear me?
Yes, I can hear you.
Okay, Assalamualaikum and good afternoon, everyone. Okay, thank you for still being with us. Okay, now I would like to introduce our next invited speaker, Dr. Bambang Purwono. Okay, first of all, I would like to share a little bit about our speaker today. Okay, Dr. Bambang's obtained, okay, can you go to the next slide? Okay, Dr. Bambang Purwono obtained his Bachelor of Science from UGM in 1986, then followed by Master of Science from University of Salford and PhD from the University of New South Wales. Okay, Dr. Bambang started his career as chemistry lecturer in 1987 at Department of Chemistry, Universitas Gadjah Mada, and besides, he was also an assistant vice rector in the corporation field, UGM, from 2000 to 2012, and his research interest is in chemosensor and biological active compounds. So far, he has published 137 article in reputable journal with H index of 11. Okay, and the latest publication in 2020 in Indonesian Journal of Chemistry with the title of Design of New Quinazoline Derivative as Epidermal Growth Factor Receptor Inhibitor through Molecular Docking and Dynamics Simulation, and also has published in conference and workshop proceedings. And Dr. Bambang current research project, which is related to the presentation topic today, is the synthesis of antimalarial and chemosensors. Okay. Without further ado, I would like to invite Dr. Bambang to share with us his work entitled Organic Synthesis for Sensor Molecules. Welcome, Dr. Bambang.
Thank you very much for the moderator. And okay, can you see of my slide? You can see
yes,
my slide
yes,
already? Okay,
yeah,
right,
we can see your slide.
Okay, thank you very much. Okay, thank you very much, ladies and gentlemen. First, thank you for this organizing committee to give me opportunity to share of my research is about organic synthesis for the sensor molecule. Before we start off this presentation, I would like to have the same idea what is the chemical sensor. According to the IUPAC, we know that the chemical sensor actually is device. Is device and then give chemical information, very specific sample, and then and to use as an analytical usable of the signal. Yeah. So I mean this because of device. So this device can deliver a real time and then online and then specific compound of ion even from this complex sample. Yeah. Because this very lot of the definition, the chemical sensor, but we are working with the compound. So there is another definition about chemosensor, which is actually the compound, yeah, can be detected of analyte, yeah, and then after interaction, they give of the signal and the signal chain as absorption or maybe emission or maybe redox potential or electrochemistry sensor. This chemosensor actually has been used of many brain, especially environmental and for monitoring and food analysis, medicine, industrial agriculture, and also can be used for the to detect of toxic gases and also explosive material. And then actually the compound of can be used as chemosensor. Yeah, this is the scheme how the chemosensor working, that we have of such a compound using consists of receptor unit and also the signal. Yeah. After they interact with analyte and then give off this the colorimetry, so they can give a color change. If the colorimetry and then the different is in the fluorescence. Okay? Okay, and then this one example that the natural dyes, for example, for the curcumin has been used of a chemosensor. Yeah, especially for this the sticker sensor from the stream freshness. When we have a stream is still fresh, the color is yellow, but after the spoilage and then the color is changed of the red. This sensor is working based on the pH change from this the situation in the in the top of this stream. Yeah. And then after that, yeah, actually my research based on the vanillin as a starting material for the chemosensor synthesis. Why? Because this in the vanillin we have the vanillin have has of the OH here, so they can use of the binding site, and also the carbonyl can be used for the extension of signal unit. And then one in the the free auto position here, so we can use to enhance selectivity. When we put up some electron withdrawing here, for example, nitro or maybe also whatever, and then the increase of the acidity of this the phenol one, so they can easily interact with another analyte can be as a base. So they can use a acid-base interaction. Yeah. This is this material that we use to synthesize of many chemosensor. Yeah, and this part there, in this presentation, I will divide with two parts: chemosensor for anion and then chemosensor for the molecule, which is formaldehyde and amine. Yeah. As you know that actually my first journey about the chemosensor started when I tried to synthesize of this indicator for the titration. When I have of vanillin and then I change I make of this the ISO one, and this is the imine, and then after we have this compound number one, and then when we make a solution and then we put in different pH, and then the color is different. So we thought that it is useful for this pH indicator for the titration. And then when we try, and then we compare with the phenolphthalein for the titration between sodium hydroxide with the acid, and then we know that the results, so that my indicator is number one, similar with the phenolphthalein result. So that it can be used for this pH indicator titration. But after that, and the pH indicator usually based on acid-base reaction, and then we try another anion, when we have the vanillin, and then we change to become the chalcone, and the chalcone, and then when we try it interact with some of anion, and then this one is with a fluorine, and then with cyano, and then carbonate, and then sulfate, they give the different color. Yeah, and this color when there are no anion, the yellow, and then after interact with anion, they give of the red one. Yeah, and then to make what happened the interaction. This one we use of computational chemistry to see that the interaction, and then when we give the color, the interaction NSC interaction is very high. Yeah, and this one and this one. Yeah. So actually, this work also has been supported by the computational chemistry. Yeah. This is from the anion, but we are not happy with this one because I mean when we work with the sensor, should be selective and also sensitive. But in this case, we have three anion, giving the result. It means that it's not selective enough. And then we try to make another compound which is very selective one. And then we try to have another compound which is we use this is also still the vanillin, and then the carbonyl we change to become the nitromethane. Also, we put off the electron withdrawing here. We hope that with a long of delocalized system in this compound, make of a very clear color change. However, the result is you can see here. Also still not selective enough. So mean also the fluorine one. And then the D is iodine. Iodine also give a positive one, and also the carbonate. And also from this, the compound number 2 also is not selective enough. Even the give of the different color of the color change. And then we try also the different compound. We use actually after we have the chalcone, and then the chalcone we change to become the pyridine derivative. The pyridine derivative. Also we start from the vanillin as well once again, but after the positive with cyano, and then carbonate, and then carbonate, and then acetic acid. But in this, when we have a heterocyclic here, not only colorimetric chain, but also the fluorimetric chain. Here we go. This is not interaction, and then after that the interaction. The fluorescent is gone. And then after that, we thought that the fluorescent as caused by the use of heterocyclic compound here. And then so we make of some heterocyclic compound to become a chemosensor. In this case, we have a benzimidazole derivative start from the vanillin as well. To become benzimidazole. And then this without any interaction yellow, but using the this one is fluorine again, and then cyano, and then phosphate. Give of still not selective enough to have a one anion. And then we also try with benzoxidazole. For the colorimetric, we have a brown after interact with cyano become green yellow, and then this compound, when we change with different heterocyclic, this can have of colorimetric, and also we have of the fluorescent. So this compound actually can be used of dual mode between the colorimetric and fluorometric chemosensor. Once again, but it is quite selective enough because of this cyano. Okay, and then as I mentioned before, that this vanillin, and then we can extend to become the heterocyclic here, the tetracycline. As we mentioned before, that this heterocyclic, we hope that also give fluorescent, and then so not only fluorescent but also colorimetric. So we have a dual mode on this one, but we hope that we're very selective enough. The result after we interact with some anion, you see here, now F is negative, but we still have two compound, cyano and acetic acid, as we confirm by the spectra here, only cyano and anion of acetic acid, This is only positive into anion. But this is very selective. We synthesize the azine compound using from this vanillin with nitration here. But this compound is very selective now. Only sulfide will give a positive, but other anion did not give of the result yet. So this compound is very good, very selective enough, and for to detect of the sulfate anion. Okay, and then this confirm only as sulfide, but other is not giving, and also this very linear with the increasing of concentration, so we can use to detect this sulfide anion maybe in water or whatever. Yeah. Okay, this one is good, the correlation, and also we try not only use in the solution, but also we try in the strip of paper when we have a filter paper, and then we dip into our compound, and then we dry. After that, we interact with some sulfide. Yeah, it is the color change from this brown to become yellow one. Yeah. Okay, next, and this on the second part is about formaldehyde. Yeah. Why formaldehyde is very important? Because some of, the ripening, for example, in apple, apple, and then after dematuration, we will produce of some aldehyde. Yeah. And also, some formaldehyde is still used inappropriately to extent of the food. Yeah. And also, actually, the formaldehyde also is associated with some of human diseases. So mean that if we have a chemosensor for detection to detect a formaldehyde, I think is very useful. Yeah, our first strategy use of the pyridine, yeah, and then we put up some of amino here, so the amino can react with the formaldehyde to get imine, yeah, and then the results see that this result from the colorimetric. Yeah, without, the colorless after interact with some formaldehyde, so they give of yellow one, yeah, and also giving of different of fluorescent, yeah, giving of fluorescent from this. There is no fluorescent after we interact with the formaldehyde, they give of the fluorescent, yeah. And also we try, yeah, to make a more of amino group here, yeah, more group amino, yeah, here, and then we try to interact to use of formaldehyde for the detection of formaldehyde, and the result is is now what we see here. This compound only give of different the fluorescent without any positive on colorimetric. You can see here the difference is when we have of no interaction. This fluorescent after we interact as different emission, and then when we try to use of in a strip of paper, yeah. This is the A is about we put in the with the paper. After that we see in this port table of UV, and then we interact with the formaldehyde with the change of the color, and also we try to this is the formaldehyde, and then this is a formaldehyde in a mid-pole. Yeah, so this compound also can be used to test of formaldehyde and the mid-pole test. Yeah. Okay, yeah, and then also we have try to have enzyme here, yeah, because this compound is so very interesting, yeah, and then we use of still amino here, yeah, yeah. This will give a colorimetric, yeah. First is yellow after we interact with some formaldehyde, we get the change of the to become a red one, and also give of our first without any formaldehyde, we give a fluorescent, but after interaction, the fluorescent is slowed down. Yeah. So they call sometimes they call of the mode of what we call on off mode for the fluorescence. Yeah. This is from the design. Yeah. Yeah, also we try, yeah, use this, this compound and the paper strip once again. Yeah, this is, we tried, we interact with, with formaldehyde, this is in the naked eyes, yeah, but, and we check in the fluorescent, yeah, so they give of different, also different color. So we know that, this as a paper strip with this compound, so that we can test of the formaldehyde. Yeah. Okay, and this also once again about the chemosensor for amine. Yeah, why amine so important? Yeah, because this amine actually can be seen some of mid deterioration process of amine. Yeah, there are two things that total volatile amine, yeah, is produced, and also pyogenic amine. When we have spoiled of meat, so we can see that the value of total volatile basic nitrogen and pyogenic amine will increase. Yeah. So we try to synthesize the chemosensor to detect the freshness of the meat. Yeah. And then we try, yeah. Also, we still use of this basic of calcone and also coumarin, yeah. And then we start also from this what we call calcone, coumarin from the vanillin, and then when you use here the collagen, it can detect of this ammonia, the P ammonia, the C is butylamine, yeah, also diethylamine and 3-methylamine. So mean the ring of we can detect ring of amine. So mean that we thought that this compound number 2 can be used as amine for the amine detection. Yeah. Also we try, yeah, and then we when we have meat mean spoiled, and then we the pH is will increase, and then this compound also can follow the increasing of pH from the meat of deterioration. Yeah. Okay, and also we synthesize hydroson, yeah, hydroson also from this from once again from the vanillin, and then hydroson, 2 hydrogen here, hydroson here. But when we have of just the hydrogen, they do not give of collagen, but when use of nitro one, so they give under different color when they interact of a ring of amine. Yeah, start from ammonia, dimethylamine, triethylamine, yeah, yeah, and also with the butylamine and so on. Yeah. Okay, when we use as to detect of the meat after this the keep in the room temperature, yeah, and then they can see here, yeah, they can detect of the color change up to 24 hours, yeah, and also when we use the extract of meat, preparation of extract of meat is very clear that 24 hours in the room temperature, the meat is deterioration. Yeah, not only using of the solution, but also we use of strip paper here. Yeah, so they can detect. Yeah, yeah, this can detect the difference of the color. Yeah, the different color after 24 hours. Yeah, keeping the color is different. Okay. Yeah. Okay, we try with another imidazole using the nitro one. Yeah, but the result you can see here. Yeah, the color is not very. The color is not very different. Yeah, just the the intensity. Yeah, ring of using of from the ammonia, butylamine, diethylamine, triethylamine. Also, when use of the paper strip, the color is not different. Yeah, maybe we thought that maybe the nitro is not enough as a strong electron withdrawing. And then we try to replace the nitro to become the SO1. Yeah. However, yeah, when we try to the association of this imidazole, but the result is is very very unusable. Yeah, because we lose of dimethoxy here. Yeah, even the ISO is can give the ISO1. And in fact, that in the deassociation reaction, yeah, we found also that in this, you can confirm that there is no methoxy in this here. Yeah, also this the proton one, and also from this carbon, yeah, also this there is no peak here. Yeah. Okay, and then why the loss of the association? Yeah, we found that also actually is very common. That the association is very sometimes we lose of the methoxy one. Yeah. Okay, but the result, even this result, the hydroxy we try to see if this as amine sensor. You can see here, yeah, the amine this compound also still give of this different color. Yeah, so mean that we can use this compound can be used as a chemosensor of amine, ranging of ammonia, butylamine, diethylamine, triethylamine. Yeah. And also we compare with the sodium hydroxide, and so the color is not very big different, and also from this the IR. So mean that from the mechanism here, yeah, I mean the interaction ammonia with this compound is with the deprotonation. Yeah. Okay, the summary, vanillin can be used as starting material of many types of chemosensor, and then the electron withdrawing group, yeah, can be used to increase sensitivity, and also selectivity. Chemosensor depend on spatial signal unit of the group, and application of a chemosensor solution is more sensitive than in paper. Yeah. In this opportunity, we thank to my student, Sylvia, Ahmad Hanafi, Oyun, Eswarma Dahawati, Nurul Dadang Arfiani, Eka, Linggayani, Peta, Trisno, Diana, Nevi, who work with most of this compound. This is my presentation. Thank you very much for your attention.
Okay, thank you very much for very interesting presentation on the chemosensor for various applications. Okay, now I open for question from the floor. Any question, you can raise your hand, or you can straight asking here, and also you can type in chat box. Okay, I ask a question, this Bambang. Okay. Okay, since from the conclusion you said it's more sensitive in solution form, is it any planning to make it in the form of solution to be portable device?
Yeah, because maybe it's because of the solvent depend. Yeah, sometimes so. This is still my work, how to make up color change when we have solid metric. Yeah, because in solid, so there is no solvent who can increase to enhance of the color change. This is like because of the sulfatochromate. Yeah, maybe we can mix with some solvent. We embedded in the filter paper. Yeah, so the solvent function still there. Yeah, even very small. So to just increase of this selectivity.
Okay, thank you, doctors. Any question from the floor? Okay, we wait for a while. Okay. Okay. I think that the Bambang, so far no more questions. Okay, I will end our presentation session. Okay, thank you very much, Dr. Bambang, for your very interesting presentations. Okay, now I pass back to the MC. Thank you. Assalamualaikum.
Thank you, Dr. Bambang Purwono MSc, for the great presentation, and also thank you to Dr. Mardiana Said for moderating the session. Ladies and gentlemen, there are a few sponsors which support this event. One of them is PT Ara Mitra. This is the introduction video of PT Ara Mitra, and after that, the committee will play profile video of the international undergraduate program in chemistry of Universitas Gadjah Mada. Please enjoy.
We are living our life, and chemistry is in every part and moment of our life. Chemistry is an important branch of natural sciences that helps shape our current modern life. Advances in chemistry will lead to the development of new drugs, renewable energy sources, clean water supply, safe food, and many more. Upon graduation, our graduates can find a profession related to chemistry in many areas such as education, research and development, chemical and petrochemical industry, agriculture, mining, and many more.
Hello and good morning. My name is Roto. Welcome to the Department of Chemistry, Universitas Gadjah Mada. This is the home to 44 teaching staff and more than 700 students. We are the best chemistry department in Indonesia. The International Undergraduate Program of Chemistry was established in 2011. The language of delivery is English. The alumni of this program now working in multinational company across Indonesia. Currently, the class size is 30 students. The benefit of International Undergraduate Program. First, English is the language of communication, small size of the class, and thesis is written in English. To join this program, you should have English proficiency and good standing of high school record. Please come and join us.
The students are provided with a spacious and comfortable student lounge. In here, the students are welcome to conduct any meeting, study group, self-study, or just simply rest and chat in between class hours. The chemistry department has its own library with internet accesses. Thousands of books are available in the Library of Chemistry UGM. More than 30 subscribed based of international chemistry journals are also available. Our facilities coexist with the natural environment in providing comfortable informal areas for learning, gathering, and networking. We extend teaching environment beyond the building interiors and onto the campus grounds when nature meets brand new ideas. We also provide laboratory facilities for students to conduct practicum and final research. The final research is performed at the physical, analytical, organic, and inorganic chemistry laboratories with additional teaching laboratories of fundamental chemistry. It is also home to the Austrian-Indonesian Center for Computational Chemistry. An array of international standards of research equipment such as transmission electron microscope or TEM, a major equipment to support nanoscience and nanotechnology. Organic elemental analyzer or OEA, gas chromatography, gas chromatography mass spectrometry or GCMS, high performance liquid chromatography or HPLC, and Fourier transform infrared spectrophotometer or FTIR.
Hi, my name is Alfia Dia Shabria. People usually call me Fia. I was in International Undergraduate Program of Chemistry, specifically in Organic Chemistry. One of the best opportunities of mine was to study in IUP Chemistry UGM because it provides a very supportive environment such as a best and professional lecturers, a very cooperative friends, good staff, and adequate facilities such as classes, libraries, lunch, and of course a complete laboratory that support me to study harder and more focused.
Selamat pagi. Hi, I'm Emma and I went to UGM for the exchange student program.
Hi, I'm Via. I'm a graduate of IUP Chemistry, Universitas Gadjah Mada, batch 2016. I still remember the great experience while studying in UGM. What I like the most about the IUP program is the intensive small class, which makes the teaching and learning process very effective. The lecture and other college really builds an interactive learning environment with presentation and some group discussion. And during the exam period, students are always facilitated by extra classes for exam preparation. In addition, the attractiveness of Universitas Gadjah Mada as a whole uni are that UGM has many partner universities abroad. I had the opportunity to do my final project research at the University of New South Wales, Australia for 3 months.
IUP Chemistry Study Program UGM.
Join with us!
Ladies and gentlemen, the next agenda, we are going to have a parallel session. After the end of the parallel session, please return to the main room at 3:40 p.m. Western Indonesia time for the closing ceremony. The participants who are not presenters are allowed to choose which breakout room to join during this parallel session. For those who join the parallel session, now you can proceed to your presentation room. Thank you. Dear participant who previously joined the G room or the Gamma room, you can choose which breakout room you want to join. Thank you.
Tapi nggak ada padekan kalau
Ladies and gentlemen, we have come to the end of our occasion. As a sign of appreciation, we come to the best paper announcement. We are pleased to announce the 5 best papers. An evaluation committee, for best papers. An evaluation committee considered the originality and significance of the papers in determining the winners. I'd like to invite Dr. Muhammad Idam Darussalam Marjan to announce the best papers. Please welcome Dr. Marjan.
Okay, so thank you very much, Mas Fadli, for your kind introduction. So, Bapak, Ibu, ladies and gentlemen, good afternoon. Yeah, so Assalamualaikum warahmatullahi wabarakatuh. So we have arrived at the announcement of the best paper award. Yeah, so for information, we have okay, for information, we have received as much as 54 papers, yeah, coming from different fields of chemistry, and from the evaluation, yeah, of the papers, yeah, on behalf of the scientific committee of the ICCS 2021, yeah. So we will decide, yeah, we have decided the best paper award at the 4 topics of chemistry. So the first one is analytical environmental chemistry. The second one, inorganic and material chemistry. The next one is organic and biological chemistry, while the last one is physical and industrial chemistry, as well as theoretical and computational chemistry. So for the last topics, yeah, it's a combination of 2 topics, yeah, because there's not much paper on that field. So we combine these 2 topics into one big topic. Okay, please allow me to introduce the scientific committees for the ICCS 2021. So we have Professor Dr. Indriana Kartini from Universitas Gadjah Mada, Dr. Mardiana from University Sains Malaysia, Dr. Roto, Dr. Dwi Siswanta, Dr. Tutik Dwi Wahyuningsih, and me, Dr. Idam from Universitas Gadjah Mada. And we have discussed about the paper and the points of evaluation for the best paper award. Yeah, we consider the novelty, the quality of the data, and the discussion and presentation of the data of the manuscript. So based on this evaluation, we have decided 4 winner for the best paper award. Yeah, and the winner will obtain the certificate for the best paper award, and also the award as much as 1,500,000 rupiah. Yeah, so let's go. Without further ado, let's announce the winner of the best paper award. So the best paper award goes to okay, let's see. So the first topic, the first category, the best paper in analytical and environmental chemistry goes to Masidatul Lakman Miskam with the title Deep Eutetic Solvent Functionalized Graphene-Based Ferrofluid for the Liquid Phase Micro Extraction for the fluoroquinoline from water sample. The next category, the best paper in inorganic and material chemistry, awarded to Prianga Arif, yeah, with the title of Physicochemical Study of Ketone Blended Sulfonated Polyether Ether Ketone and Graphene Oxide as Filler for Direct Metal Fuel Cell. Congratulations for Mr. Prianga Arif. The next, the best paper in organic and biological chemistry goes to Respati Tri Sumarsono, Screening and Toxicity Assay of Bioactive Compound Ethyl Acetate Extract of DCDSP from Oga Island. And the best paper for the physical and industrial chemistry, and theoretical and computational chemistry, awarded to Fitri Ika with the title of Potential Application of Rhamnoliquid Silica Nanoparticle Complex for Enhanced Oil Recovery with the Molecular Dynamic Simulation. So we have 4 winners for the Best Paper Award. Yeah, once again, congratulations for all of the winners, and also you all for the participation and the fruitful discussion during the ICCS. Yeah, and last but not least, we wish you a good luck and good success for your future. Thank you very much.
Thank you, Dr. Marjan, and congratulations to the authors of 4 outstanding papers. The last agenda is closing. Now, I would like to invite Professor Kuatriana, the Dean of the Faculty of Mathematics and Natural Sciences, Universitas Gadjah Mada, to officially close the 4th International Conference on Chemical Sciences. Professor Kuatriana, the time is yours.
Sorry. Still, and sorry. Okay, I repeat again. Hah? Itu pokoknya sebentar mas. Virtual backgroundnya
I would like to invite Professor Quatriana, the Dean of Faculty of Mathematics and Natural Sciences, Universitas Gadjah Mada, to officially close the 4th International Conference on Chemical Sciences. Professor Quatriana, the time is yours.
Okay, thank you very much. I'm sorry, our mic is still in mute position, so I will repeat again my closing remarks. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. First of all, let us thank to God Almighty, who has given His grace and guidance so that the 4th International Conference on Chemical Science, ICCS 2021, has been held successfully. And I believe that during this 2 days of the meeting, all of us had a fruitful discussion and sharings. And in this 4th ICCS 2021, whose central theme is advancing innovation in chemical sciences for sustainable development in COVID-19 era. We learned a lot from the keynote speakers, invited speakers, and also from contributing speakers who have shared their exciting works. And on behalf of the Faculty of Mathematics and Natural Sciences Universitas Gadjah Mada, I thank you all for delivering such essential research outcome so that all of us can deepen our knowledge of chemistry and other related fields. Furthermore, I would like to thank all the presenters and participants who have joined this year's conference. Through your presentation and discussion, I sincerely hope we get new strategies to improve our capability to solve the problem related to the chemistry in our own countries. Again, I would like to thank all the committee members from the Department of Chemistry, Universitas Gadjah Mada, and also the School of Chemical Sciences, University Science Malaysia, for organizing the very nice conference and ensuring it proceeds smoothly and successfully. And I would like to apologize for any inconvenience that you have made experience during this virtual event. Finally, by saying Alhamdulillah, I declare the 4th International Conference on Chemical Sciences 2021 is officially closed. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Professor Quatriana, for closing this event. Ladies and gentlemen, before we say our farewell, I would like to invite all of you to have a photo session first. To the keynote speakers, the dean, as well as participants, please take a position and enable your camera. Okay. I will count from 1 to 3, and then I will take the pictures. There are 4 slides in this event. So I will start from the first slide. 1, 2, 3, smiles. Okay, now the second slide. 1, 2, 3, smiles. The third slide. 1, 2, 3, smiles. And the last slide. 1, 2, 3, smiles. Okay, that is the last slide. Ladies and gentlemen, on behalf of the 4th International Conference on Chemical Sciences Committee, We would like to say thank you to all the keynote speakers and invited speakers who gave a great and interesting presentation. And we would like to say thank you to all presenters and participants for your participation during these 2 days. Also, we are sorry for our imperfection or mispronounce. Now, we would leave you with a quote by Stewart Brand, an author and innovative thinker, who once said, "We can see the past but not influence it. We can influence the future but not see it." Let us all be guided by all the things we have learned and heard throughout this conference and be able to see and influence our future. See you at the 5th International Conference on Chemical Sciences. Good afternoon and wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Prof. Rohana, Team USM. Thanks a lot.
Thank you.
Thank you, Prof. Rohana. Thank you very much. Alhamdulillah. Dan
Inshallah, we see again in
Thank
Penang,
you.
ya, Pak?
masih Prof. Rohana masih ada.
Inshallah. Assalamualaikum.
Inshallah, see you then.
See you.
ICCS.
Take care. Yeah, ICCS. Yes. See you, Bu.
Thank you.
Thank you. Bye-bye.
Assalamualaikum. Aduh, dah aku